Okay, so thank you for being here. This work is done in collaboration with loads of institutions, as you see here. So the theory has been done between the University of Edinburgh, where I'm based, and some universities in Paris, Telecom, Paris-Tech, Paris Diderot, and CNRS. And the experiment has been done at the quantum group at the University of Bristol in collaboration with some other universities as well, the University of Bath and the University of KwaZulu-Natal. So this work is about how we can witness entanglement in a network that consists of some agents that are either trusted or untrusted. This can be done using verification protocols for distributed multipartite entanglement. Specifically, we're going to use a specific type of entanglement, basically GHZ states. Now, the experimental implementation, what we do is we create some photon pairs using microstructured photonic crystal fibers, and then these pairs are fused together to create 3-photon and 4-photon GHZ states. So the model is the following. What we consider is that we have a source that we do not trust. It's supposed to create and share amongst n parties a GHZ state G0n, which is basically the 0 plus 1 state. Now, we also consider that we have several parties which share this state and we do not trust them. So we do not know how many of these parties are untrusted. We have an unbounded number of parties. And they can also collaborate between them and collaborate with the source in order to convince us that we are actually serving a GHZ, while in fact we are not. We assume that the honest parties trust their measurements, so they have a trusted qubit, single qubit measurement device, and that they can also communicate between them in a secure way. So they share pairwise private classical channels. They have classical communication between them that is secured. So the protocol goes as follows. The source shares a state rho with the n parties. So this state is shared, and one qubit is sent to each of these n parties. Now, one of the players, which we're going to call the verifier, and let's suppose that is the first one, actually selects all the inputs for the rest of the parties. So he selects some angles theta j from 0 to pi and sends them to each of the parties. There is a condition on the inputs that their sum needs to be a multiple of pi. So it needs to be either 0, pi, 2 pi, etc. So each of the inputs goes to the players in a secure way. And then each party, depending on this input, measures in a basis that is defined by two orthogonal vectors on the xy plane. So they use this input to measure in this basis on the xy plane. And then they send their outcomes yj to the verifier via the private channel. So each of the players measure and send the y's to the verifier. And then finally, the verifier gathers all the outputs yj and performs a test t, which basically consists of checking a condition on the inputs and the outputs. So what this test actually means is that when the verifier has chosen inputs that are an even multiple of pi, so basically it's 0, 2 pi, 4 pi, etc., then what he's expecting to find is that the parity of the outcomes is 0. Now, on the other hand, when the verifier has chosen inputs that are an odd multiple of pi, so pi, 3 pi, etc., then he's expecting that the outcomes have a parity 1. So the first property that we want to check is that our test actually works. So it works on the correct state. So it should always succeed when the state that is shared is a GHZ. So what we can see all the measurements as equivalent to a rotation around the z-axis, followed by a measurement in the Hadamard. So we can think of them as total measurement that is a rotation around on the xy plane, followed by measurement by all the players on the Hadamard basis. So from the condition on the inputs, we have two cases. As I said before, we have the first case is that the sum of the inputs is an even multiple of pi. And what this means is that when we rotate the GHZ set by by 0, 2 pi, etc., then the GHZ state is mapped to itself. So it goes back to the GHZ. And when we measure the GHZ in the Hadamard basis, what we get is a superposition of strings that have parity 0. So we see that the condition that the test basically passes for this specific case, because we get a 0, and then here we also had a 0 to pi. Now, in the second case, the sum of the inputs can be an odd multiple of pi, right? So it can be pi, 3 pi, etc. Now, when we rotate the g at z by pi, then the g at z is mapped to an orthogonal state, which is actually the 0 minus 1 state. And when this state is measured in the Hadamard basis, then it gives a superposition of strings that have parity 1. So again, the condition on the test holds, because here we got 1 and here we got pi. So what I have shown you here as the test actually holds for both cases. So when the correct state is shared by the source, the test always succeeds. Now, the thing is, what happens where the source actually shares a state that's not the g at z? So when the state that is shared is a state rho that has fidelity with a g at z phi, then we can actually show that we can upper bound the probability of the test succeeding by a function of the fidelity. So this function is actually half 1 plus the fidelity. And how we show it is by assuming that our test is, by thinking our test as equivalent to performing a P of M. This P of M, Pn, can be shown to be this one. So this actually means that our test always succeeds on the g at z. It never succeeds on the orthogonal state, which is a 0 minus 1 that I showed before. And it passes with probability half for the rest of the states that are in the space orthogonal to these two states. And then it's not very difficult to see that this probability can be seen as doing this P of M on our state, and it's actually upper bounded by this expression. So this is in the case where all the parties are doing what they're supposed to do. They're measuring the state with the correct measurements. Now, what is happening when some of the parties are not doing what they're supposed to do? So what if we allow some of the parties to do some operation on their space in order to bring that state as close as they can to the g at z? So we need here to consider, let's say, a maximized fidelity, which is going to be this phi prime, where we allow the dishonest parties to do an operation in their space and bring this state as close as they can to the g at z in order to maximize their probability of passing the test. Then again, we can upper bound this probability by a function of this maximized fidelity, which is a bit different than before. It's 1 over 4 times 3 plus this fidelity, this maximized fidelity. So I'm not going to go through the proof, but it's basic. The proof is actually based on doing this Hellstrom measurement on the state and trying to distinguish between the two correct states that the honest players are expecting to find. But I'm not going to go through the details of the proof just now, because I want to show you this sketch of the implementation that has been done in the University of Bristol. So this is basically the only slide that I'm going to show you about experiments. It's a sketch, and if you want some more details, you can check out this article by Breen et al. From 2012. So what is happening here is that we got the photon source. It sends some photons in a Sagnac source. Then this creates some photon pairs there with different wavelengths, an idler and a signal pulse, and they get split up in the dichroic mirror, and then they get fused in a PBS and sent to the different players. Then the players use their wave plates to measure in the required basis. So what is very important in this experiment is that everything is automated. So these wave plates are actually measuring very quickly in different measurement bases. And this is also done in a single shot way. So it's every time one photon is measured, then this gets instructed automatically to switch and change in a different measurement basis. So this is the way we create a 4-photon g at z state. We're actually going to use a 3-photon g at z state as well. And what we do is a slight modification of the setup. We basically don't use the second Sagnac source. There's no, the photons are only pumped one way. So basically there's only 3 photons that are created here, entangled photons, and this actually gives a slightly higher fidelity. So the tomography results of the creation of the GHZ states are these 4 figures for the 3-party GHZ and for the 4-party GHZ here. This is the real part and the imaginary part of the actual implementation. This is the theoretical GHZ state that we're expecting to find. And here again is the real and imaginary of the 4-party and the theoretical ones. We see that the fidelity is 0.8 for the GHZ3 and 0.71 for the GHZ4. So the measurements that we did on our states are the following. We actually ran 2 types of protocols. The first one was what we call the XY protocol. This is a simplification of the protocol that I showed you before, which I'm going to call the theta protocol. So the XY protocol is basically just doing the merming game or pseudo-telepathy game. We, instead of choosing arbitrarily angles around the XY plane, we just choose X and Y measurements. So this protocol has been also analyzed in a previous work by by myself and some co-authors. And what we did for both of these protocols is first we ran the honest case. So we just created the correct entangled state and we measured the measurements that we were supposed to. And then we tried to see what can happen in the case where there is no entanglement, no multi-party entanglement. So what we did is we disentangled one of the players. We created a separable state, and then we tried to see how can the dishonest players maximize the probability of passing the test and convincing us that we share a multipartite entangled state. Well, in fact, we don't, and we share a separable state. So we did this for GHZ3 and for GHZ4. And so this slide has all the measurement results that we got from our implementation. So the first 2 are for the 3-party GHZ, then the last 2 are for the 4-party GHZ. So what we see here, this straight line here is what we have for the honest case, so when everyone is doing the correct measurement results. What we have for both the X, so all the blue lines are the XY protocol and the purple lines are the theta protocol. So here we see the straight line is the pass probability for both protocols is around 0.83, 0.84. So this is when all players are sharing a 3-party entangled state. Now in the case where we want to check a separable state, so we want to check the dishonest case, what we did is we had one party measure in X. So he disentangled his qubit from the honest parties. And we see here in figure B what is happening with the pass probability. So when we range from the dishonest angle from 0 to pi, the pass probability, instead of being a straight line here, exactly because the dishonest party is unentangled, goes down to actually half for pi over 2. So what we need here in order to find the pass probability is we need to integrate this whole thing, and we get the value of 0.723 or 0.736 for the XY protocol. So here, this is, I only show you the theta protocol where the range, the angle ranges from 0 to pi, but for the XY protocol, you only have 2 values, basically X and Y, and it's just here and here. So we see that the pass probability for the dishonest case, for the unentangled, for the separable state, is far less than the pass probability for the honest case, what we would expect to have if we had a 3-party entangled state. But what is interesting here to see is that if we start thinking about experimental imperfections, if we start thinking about a proper experiment, we're going to have to start thinking about losses. And if you consider that the honest parties are willing to accept some losses in the experiment, if they are willing to accept, for example, 20% loss or 30% losses, then this could work in favor of the honest parties. So what of the dishonest parties. So what the dishonest parties could do is that they could use this willingness of the honest parties to accept losses and replace their lossy equipment, if they could, with perfect ones, and actually throw away some of the bad input. So what they could do here is start from the pi/2 angle. Whenever they got a pi/2, start saying, oh, I lost this input, and then only play with the probabilities that are pretty high. So if they had, for example, if they could announce 50% losses, then they would just throw away all these angles here, and they would just increase their probabilities. So what would happen here is that by increasing, let's say, the loss rate that the honest players are willing to accept, the dishonest parties can increase their pass rates, their pass probabilities. So again, this purple line is the XY, the theta protocol, and the blue line is the XY protocol. But the very important thing here, and the reason why we actually introduced this new protocol, this theta protocol, and we didn't use the XY protocol that was already used a long time ago in pseudo-telepathy and in self-testing and in the Mermin game, basically, the reason why we started using it is because the XY protocol seems to be not tolerant to losses for more than 50% loss rate. So when the dishonest players can throw away half of their inputs, so if they only play with X and Y and they can throw away the Y and only play with the X, for example, then they can always cheat. They can always convince the honest parties that they're sharing a three-party GZ state. While in fact, if we're using the theta protocol, then we can have an almost loss-tolerant protocol, and we can go up to almost 100% loss tolerance, because exactly we have a continuous choice of inputs. So we see here that while the blue line goes directly to let's say, the honest rate, then the purple line goes asymptotically close to there only for 100% losses. And this was the reason why we introduced the theta protocol, but actually what happened is that we also got a second advantage because of our experimental implementation that gives us this straight line here. So these solid lines here actually show the genuine multipartite entanglement bounds. So in order to be able to be sure that we got three-party entanglement, we need to be above these lines. And this green line here is the XY protocol. Again, the purple line is the theta protocol. And we see that our experimental values are below the XY protocol, but just a bit above the theta protocol. So actually, with the experiment that we used, if we were using the XY protocol, the previous protocols, we wouldn't be able to verify in the dishonest case that we got three-party entanglement. While with our new protocol, we can actually show, even for like small percent of losses, we can actually be sure, even when we don't trust any of the parties, except of course the verifier. We can, here, of course, we got two honest parties, one dishonest. We can actually verify that they do share three-party entanglement. Of course, if we had a better experimental implementation, we would increase this line here. We would be able to tolerate more losses, for example, and then get better results. Of course, the same thing cannot be shown, unfortunately, for the four-party GZ because we don't have that good fidelity. So we say that we are, for both the protocols, we are below the GME bound, the genuine multipartite entanglement bound. So to conclude, what I've shown you is some protocols to verify GZ states against dishonest parties. We've also done some fault tolerance analysis. And in collaboration with the Quantum Group at Bristol, we've demonstrated our protocols using some single-shot automated systems. Now, there are some open questions. For example, can we do the same thing for other states, like, for example, for graph states? And how would we be able to use this type of protocols in order to do some further multi-party computation, for example? So that's it. Thank you.
Thank you. And now the session is open to discussions. Oh.
Thank you. Why should we trust the verifier, or said otherwise, how is the verifier selected by the by whatever process?
So this is how we build our protocol, that we suppose that we have a verifier, but we can actually iterate the role of the verifier. So we could have a way of maybe if we're trusting, let's say, a majority of the players, then we can somehow have like a leader election, or we can like iterate between them and have some upper bound, which is not going to be as good, but we could have some upper bound on the probabilities.
Yeah, but I thought that one of the interests of this was that it does you don't need to require a majority of honest player, but you would just to choose the verifier is kind of sad.
We could even if we had one honest verifier and then the rest of the dishonest players, when they were verifiers, their turn to be verifiers, they had pass probability of 1. Then again, we would have something which would be less than 1. So it wouldn't be that good, but it would definitely be less than 1.
Any other questions? I think in the theory you assume, say, each receiver has a qubit, right? On the other hand, in the experiment, I'm pretty much sure the detector is threshold detectors, right? On-off detectors.
Sorry, the?
Detectors are on-off detectors or threshold detectors, which just distinguish between no photon or one or more photons.
Yeah, so I think that this is done by post-selection. So you only have a 4-party or 3-party GZ state when you only detect 4 photons, like 1 photon each.
Oh, I'm wondering the possibility of dishonest sender. If it's going to use multi photons in a single pulse to somehow deceive the.
It doesn't. So you're saying that if the source is dishonest, it might send more photons.
Yeah.
This wouldn't actually matter. I mean, because when we think of the dishonest players, we actually think of them as one party. So it could even be, even if you have 5 dishonest parties, then you can even think of them as one that have 1 photon or 1 state. It doesn't really matter if they're sharing more photons than that. What they actually can prove is that they are entangled, that all the honest parties share the correct entanglement between them, and they are also entangled with the bunch of dishonest parties. So not with each one individual, because we can't really control what is happening in the dishonest space.
Okay, thank you. Okay, any other questions? If not, then let's thank all the speakers in this session again.